Hello, everyone. My name is Ziyi Zhou. I'm a graduate student working at Laboratory for Intelligent Decision and Autonomous Robots at Georgia Tech. Today, I'm very happy to present our ACC paper. The title is Accelerated ADMM-based Trajectory Optimization for Leg Locomotion with Coupled Rigid-Body Dynamics. Nowadays, the leg robot is arousing more and more attention because of their abilities to achieve highly dynamic motions, such as jumping or even backflipping, as they can traverse very rough terrains that mobile robots can never reach. Following a hierarchical planning structure, we usually have a task planner as a top layer, which provides us high-level inputs, such as moving from A to B in a cluttered environment while avoiding collisions with dynamic obstacles, or achieving a specific motion, such as walking or running. Then the trajectory planner will generate the joint space trajectories, followed by a tracking controller to finally achieve the motion. This paper mainly focuses on the trajectory planning level based on trajectory optimization. Trajectory optimization approaches have been investigated extensively in the field of dynamic leg locomotion. However, the optimal control problem of underactuated switch system with high degrees of freedom commonly suffers from intractable computation complexity. To address these issues, most existing results use a hierarchical approach. They firstly solve the locomotion problem based on a simplified model such as linear inverted pendulum or centroidal model. They use a whole body model to generate the joint space trajectories. However, this mismatch between simplified and whole body models sometimes can lead to tracking problems and even locomotion failures. Overall, our work centers around the dynamics consensus between a centroidal model and whole body model to account for full dynamics while still maintaining computational efficiency. Starting with full rigid body dynamics with a floating base, we can use the centroidal model to get an exact mapping from full model to the center mass level. From the equation inside the bottom left block, we can see that the linear and angular momentum can be derived by the external forces, center of mass position, and contact points. However, as you can see, it depends on the full model to compute the center mass position and contact points. To get rid of the dependency on the full model, we need to assume that the momentum produced by the joint velocities is ignored. Therefore, the complexity of optimization reduces significantly by planning on a simplified model. However, sometimes the angular momentum produced by the lower limbs matters when trying to achieve highly dynamic motions such as running. So it is also important to account for the whole body dynamics, which the simplified model cannot capture. To address this mismatch, we need to firstly formulate the problem. The objective is to minimize the summation of whole body cost and centroidal costs. As we discussed before, the dynamics for whole body and centroidal models need to be satisfied. The dynamics consensus is achieved by constructing equality constraints between center of mass, linear momentum, angular momentum, and contact forces. The joint positions and velocities will be mapped into the center of mass level to create such equality constraints. In addition, we have some inequality constraints for the joint limit, torque limit, and friction cone. The core idea of our approach is to make use of a distributed optimization method called alternating direction method of multipliers, ADMM, to further decompose the original optimization structure into multiple easier problems to solve. We will get back to this framework later. Based on the discussion above, the technical motivations of this work can be summarized into several points. First of all, solving large-scale nonlinear optimization with full-body robotics dynamics is challenging and computationally inefficient. To address this inefficiency, a hierarchical planning using simplified model followed by a full model can reduce the complexity. However, achieving dynamics consensus is especially crucial for generating highly dynamic motions. Also, inherent hybrid contact nature of the locomotion process enables us to explore the distributed structure of the optimization via ADMM. Thus, we aim to make use of the existing acceleration techniques to achieve better convergence rate in our own formulation. Also, the stopping criteria or equivalently convergence criteria are not clearly defined to guarantee the dynamics feasibility. Before we dive into the splitting of this locomotion problem, let's have a quick review of the ADMM algorithms. ADMM solves optimization problems in a distributed manner. The classical ADMM is used to solve an optimization problem that is separable into two objectives with a linear coupling constraint. The first step is to construct an augmented Lagrangian with a dual variable y and an augmented Lagrangian parameter rho. By a simple transformation, we can ignore the constant term and derive a simplified augmented Lagrangian using a scaled dual variable, which is compact and easier to work with. Then the problem will be solved in an alternative and iterative way. The updating sequence will be divided into primal and dual variables. Dual updates. During the primal updates, we will only optimize for the local variables and assume the rest of the decision variables as constants. A natural extension to this two-block ADMM is a multi-block ADMM. Similarly, we have more sets of variables with separable objectives, and we follow the same way to construct the augmented Lagrangian. This multi-block ADMM also contains a sequential update for primal and dual variables. Although the proof of this multi-block ADMM is still an open problem, it has been successfully applied to solve numerous real-world problems such as image processing or chemical processing. Inspired by this multi-block ADMM, we are trying to make the original optimization formulation fitted into ADMM structure. We firstly embed the dynamics inside each model, and we will let differential dynamic programming to handle these dynamics equations separately. Then we introduce more auxiliary variables, S bar, U bar, and lambda bar to create new projection consistency constraints. The new projection block is constructed by encoding the inequality constraints inside the indicator functions. In this way, the original optimization problem can be divided into different blocks via ADMM. The whole body and centroidal dynamics equation will be handled inside each block. Then the projection block will project all the related decision variables onto feasible sets. Between each block, we only pass the residuals of different coupling constraints. Given all the technical details we talked so far, finally we can have these full primal and dual update sequences. I will not go into the details, but we'll be happy to talk more about it if you're interested. Following the ADMM updating scheme, we use unconstrained DDP to solve the centroidal and whole body blocks. DDP can find local minimum for a non-convex problem with nonlinear dynamics very efficiently. By creating this new projection block, we make minimal modifications to the DDP block to preserve a good convergence and efficiency of solving an unconstrained trajectory optimization problem. The projection block reduces to a simple saturation function. When the input violates the boundary, it will be manually set back to the boundary value. This applies to both box and cone constraints. Then the primal updates will be followed by a simple dual updates, which will be performed efficiently. We also proposed a stage-wise accelerated ADMM by applying over-relaxation and varying penalty for our multi-block ADMM framework based on the practical performances. Instead of applying the over-relaxation and varying penalty at the same time, we only apply the over-relaxation at the first few iterations. After certain iterations, we apply this to simultaneously. The rationale lies in that if the varying penalty mechanism is applied from the first iteration, scaling parameters possibly make the penalty cost coefficient rho become unreasonably large. Accordingly, the convergence of local cost function for each ADMM block requires more iterations to converge. To determine when the convergence is achieved, a stopping criterion is clearly defined for all the coupling constraints. We firstly use the L2 norm of primal residuals with a tolerance similar to the classical ADMM approaches. On the other hand, since the global problem is highly non-convex and nonlinear, the local penalty costs sometimes do not converge well, even when the primal residual is relatively small. However, this problem sometimes can lead to locomotion failure since the local cost function for whole body model contains such tasks such as swing foot tracking, which is crucial to the success of whole body motions. We design an additional stopping criterion for the local cost reduction to remedy the shortcoming of using residual-only stopping criteria. All right, so here are the results. We firstly studied a simple car parking problem. The goal is to drive from an initial state to a goal state with bounded control inputs, which is a well-studied example. This example helps us to benchmark the performance of the proposed ADMM solvers. We found that under the same parameters for cost function, the ADMM solver follows a different path with lower cost compared with the control-limited DDP. We also validate a better performance of our stage-wise accelerated ADMM in terms of convergence rates. In the neat campus gained walker example, we tested our algorithm on both flat and rough terrains. We firstly demonstrate a good convergence of all the coupling constraints. The y-axis is the L2 norm of all the residuals for coupling constraints over different ADMM iterations. Note that since different constraints have their own physical meanings, each constraint will converge to a value with different levels of magnitude. Then we demonstrate that with ADMM iterations growing, the consensus of central mass trajectory between whole body and centroidal models becomes better and better. Similar to the car parking example, we also show that the stage-wise accelerated ADMM outperforms other variants of ADMM for the torque limit constraint. This also applies to joint limit and friction cone constraints in certain cases. We're currently working on implementing this algorithm for more complex bipedal walking robots like Cassie and quadrupeds. Stay tuned for more results. To summarize, we proposed a general and efficient distributed organization framework based on multi-block ADMM to achieve dynamics consensus. The inequality constraints are handled inside an ADMM subblock, which is independent from the unconstrained DDP. We also proposed a stage-wise accelerated ADMM variant to empirically improve the convergence rate of our multi-block framework. Stopping criteria are clearly defined to generate more feasible whole body motions. Currently, we're also working on a manipulation example, which shows the generalizability of our ADMM framework. The robot arm is trying to sort the packages on a conveyor belt. For each object manipulation, we use our ADMM solver to generate the motion. At the higher level, a task planner is designed to concatenate multiple motions to achieve a certain task. To end this talk, I would like to acknowledge my lab mates and our founding agency. Thanks for your time and look forward to your questions.